joined early, we do have a question to start off. So if you could go to menti.com and enter the code. There's also a direct link in the chat, or if you want to use your phone, you can use the QR code that is on the screen. And let us know how much you agree or disagree with this statement, that many organizations do not know if changes in energy consumption are due to efficiency efforts or other factors like changes in weather. All right. So we see some answers coming in, and also please keep the Menti questions open in like a browser or on your phone, because we're going to be coming back to them throughout today for some of our learning. Let's see what responses are coming in here. All right, so how much do people agree or disagree with this? Okay, so there's sort of a mix on there. This is something we see coming up a lot and will be a big focus of our discussion today on baseline modeling. All right, so we got those. As I mentioned, today we're going to be talking about understanding and interpreting baseline models. And one of the big benefits, we'll talk about the others, but is understanding, how does energy intensity, energy efficiency, how can you visualize, how can you see that independent of those day-to-day changes because of things like changes in weather. To get the most out of this workshop,
Jay, apologies. We've lost you on mute for a second.
Sorry, I'm not sure what happened there. Yeah, as I mentioned, it's intended to be interactive, so we do encourage people to keep cameras on, particularly in the breakout sessions later on. If you have any questions or anything you want to share, please raise your hand, come off mute. We do encourage people to stay on mute when you're not speaking, just to reduce background noise. And you can also, we encourage people to follow along in the participant workbook, which we will be using throughout today's session. Fatima will drop a link to that in the chat. And so please click on that link, and then at the top right, you can download that workbook to have your own copy to follow along with today's session. It contains a summary of all the things we're talking about for afterwards, but also some place to take notes for applying this to your situation, and also for some of the activities that we're going to be doing. So please download that. What we're going to be doing today, by the end of this workshop, we're hoping that you're going to be able to identify how baseline models can provide value to your work as an energy manager. You're going to learn some skills around analyzing those models to gain insights into your operations. And lastly, we're going to touch on how to effectively present your models to people who may not have taken this workshop and understand all of the in-depth details around them. Now, I did send out Jay Lee did send out some detailed information earlier this week with the reminder, some background information on baseline models for people who may not be as familiar with it or wanted a refresher. It included some terminology like those on the screen. I'm not going to get into these in depth right now, but are there any of these terms that I can clarify before we get into today's talk? If anyone has anything on here that they're not clear on the baseline models, just raise your hand or put in the chat or come off mute and share.
Yeah, R-square, T ratio, and p-value. Could you quickly go over that?
Sure. So those are statistics that are kind of built into the model. So we're not going to be covering how to build a model today, but when you do develop a baseline model, that model will have certain statistics. So the R-square is basically saying how much of the variation in energy is explained by the variation in the independent variables like weather or occupancy that you put into the model. So it's kind of like how good is the model. The T ratio and P values, their stats on each of those independent variables that will help you understand, like, are they actually helping explain the energy consumption in your facility? So we won't be getting to those in detail today, but they're basically stats that you can use to see, like, hey, is this model actually good at predicting energy? So R-squared, you want typically above 0.75. And the T ratios and P values, one of them you want small, like below 0.05, and the other one you want above 2, or the absolute value above 2. Is there anything else on here? If there's any other terms that you would like some clarification, please put them in the chat. The one thing I do want to emphasize, because it is going to come up a lot today, is that when we use these energy models, they tell us a lot about energy consumption, but everything they tell us is relative to the baseline model where it was developed or calibrated, because it's learning through a regression analysis of how to predict energy use as it's used in that baseline period. So everything we're talking about, everything we see in these models is relative to the baseline period, and it's relative to the independent variables that the model uses, things like cooling degree days, heating degree days. We're going to be touching on those independent variables and what that looks like later on, but that's just something that we're going to reinforce through today, and it's an important part of it, and hopefully that will start making sense as well later. To start off with, I want to start with talking about the value that baseline models can provide, and not just what the baseline model does, what it says, but how we see energy managers using this to really support their efforts in achieving energy efficiency. So the key ways that we see this happening are these 5, the biggest being quantifying savings. So the baseline models do a really good job of isolating energy performance, energy savings from those efficiency efforts you do, those changes you make, independent of those day-to-day changes that influence, is the absolute energy consumption going up and down. That's sort of the biggest reason why we see energy managers using models, but there's also things like identifying energy waste, supporting with commissioning efforts, project commissioning, helping with communication engagement, and forecasting that I want to touch on. So you can kind of see of like, if you're already using your model, what might you be able to do additionally with that? Or if you aren't using a model yet, to start seeing like where it could be providing value. So I do have a couple of case studies to just kind of illustrate that. So this one is from a hospital where the energy team had been active for a number of years, leading engagement efforts, behavioral campaigns, some large retrofit projects. But in 2019, the hospital leadership kind of challenged them and says like, hey, we've invested in your team, we've been investing in these projects. Why are our utility bills not going down? And you can kind of see there, it's pretty flat across those 4 years. It even increased from 2018 to 2019. The energy team had some reasons. The 2019 was a warmer summer than 2018. They had changes like increases in occupancy, shift hours, even the electricity rates had increased over that time, but they weren't really they kind of sounded a bit like excuses. So the energy team went back to their model, and using their model, they were able to show, because that model adjusted for things like cooling degree days, and had data on shifts and occupancy built into it, they were able to show that in 2019, they actually consumed less energy, even though it was more than the year before. It was less energy than they would have consumed if they had not made those efficiency improvements since 2016, which was their baseline year. So using the data as a model, they were able to show that, hey, even though our costs have been relatively flat, our bills are actually 20% lower than what they otherwise would have been. So they would have been increasing, but we managed to keep them relatively flat. When it came to identifying energy waste, this example is from a warehouse. So in September, the manager was reviewing utility bills from the previous quarter, noticed that they were significantly higher than the previous years. It had been a warm summer, but it still seemed a little out of whack. So they looked at their facility baseline model, which they had mostly been ignoring up until that point, and they saw a pretty steep increase in energy use around May. They talked to the maintenance team, and they said, oh, we did have a maintenance crew come in and do some work on our rooftop units at that time, investigate it further, and they found that I guess when the maintenance team came in and was doing the annual maintenance and doing the tests, they put overrides on the rooftop units to do those tests, but then forgot to take the overrides off. So they had been running full out all summer long. the manager was very happy to have found and corrected that error, but kind of wished that they had noticed or been paying attention to their baseline model earlier rather than having it run full out for 3 months. We also have an example from commissioning. This was from a university where in their athletics center, they were upgrading. There were 3 parallel pumps that were serving the athletics facility, and they were expecting to see some savings on the CUSUM, but when they checked their model and the CUSUM chart afterwards, it actually showed a pretty steep increase in energy consumption when they went. That happened about the same time that the pumps were installed. And when they went to look at what was causing that, they found that one of the 3 pumps had been installed backwards. So it was actually driving a lot of excess energy use. For communication and engagement, this is a really great one from a school board where a new superintendent, new board members came in and they reinterpreted a policy on like space conditioning in the schools, where before they'd only, like if someone was using the school during the summer, they only cooled it for like the portion of the school that was being used and only for the time that it was being used. But this policy was reinterpreted that, oh, if anyone is using any part of the building, the whole school needs to be cooled for that day. The energy manager objected, but didn't make much progress. But a little while after this policy change went into effect, using their CUSUM to kind of tell this story, they were able to show like how much energy increase was occurring because of this change and what it was costing the school board. So having this clear evidence actually led to a reversal in that policy interpretation, which was really great news for that school board and the energy manager. And then the last example that I have is around forecasting. It actually comes from automotive. And in this situation, corporate would send out, utility budgets for the following year to all the different facilities. The energy manager took that number and said, it's like, okay, well, if I put in next year's forecasted production and, typical weather data into that, does it line up with the budget? And they realized that it's like, oh, like this budget is actually like 15% lower than what we expect it to be based on our production forecast. And so they took this back to corporate, and it was the first time that anyone had successfully negotiated for a higher utility budget within that company. So having the data and presenting in a way of really being able to tell stories are some of the really useful things that come out of facility baseline models. So hearing those examples, and hopefully, you might relate to some of those. If we go back to Menti, and for those of you that haven't joined yet, you can go to menti.com and enter the code at the top of the screen, or you can follow the link that Fatema is going to drop in the meeting chat. But if you could let me know which of those applications, quantifying energy savings, identifying energy waste, are you currently using a baseline model for? So I'd love to hear what you're currently using a baseline model for. And while we're getting responses too, if anyone has any questions about any of those case studies that we went through, please feel free to raise your hand. Okay. Right. Some interesting results coming in. Yeah. And I think this aligns with actually, I'm surprised at the higher numbers on forecasting that's being used. That's really interesting. Does anyone who is using the model for forecasting want to share how they're using it in their organization? Because that one I expected to be lower than that. If anyone who wants to share how they use their model for forecasting wants to come off mute, I'd love to hear about that. Okay, so using it for the utility budgeting. Okay. Thanks, Luke. And what type of facility or organization are you in?
Oh, sorry, I'm in a school district.
Okay. Okay, so you use that with the schools within your district to sort of forecast the utility budgets?
Yeah, every year we put together a fairly detailed budget that's based on a site-by-site number that's all aggregated up for the different utilities and costs.
Okay, great. Excellent. All right, thanks for that. And yeah, and I do see the bulk of people responding with quantifying savings. As I mentioned, that is primary use that we see these, but there's a lot of this other value that's in there. The next question that I have still in Menti there is, which of these do you want to start or improve using the baseline model for? So were there any of those examples that you kind of thought is like, oh, I'd love to either start or improve how I'm using my model to support these goals? Okay. All right. Forecasting, right? The energy waste side. Yeah. I'd say after the quantifying savings, the identifying energy waste is probably the second most common use that we see around it. And we're going to have some really good examples or work on how you can start doing that. Great. So in order to help you achieve those, what we're going to start off with is talking about how you can interpret a CUSUM graph. So now that we know we want to get value out of this, we need to make sure that we're getting, the insights and the information out of our model that are going to lead to the outcomes that we want to see. So before we talk about how to interpret a CUSUM, could you just raise your hand if you'd like a quick refresher on what the CUSUM is? Okay, I do see some hands popping up, so I'll get to that. I also see a question in the chat on how do you address changing baselines? For example, if a building gets an LED upgrade, how would you know how to change a baseline without negating historical data? That is a really great question. And often, our general rule is like within 3 to 5 years, you should probably rebaseline on that. An example of like an LED upgrade, that wouldn't cause you to want to necessarily want to rebaseline because you want to see the savings that are resulting from that LED upgrade in the baseline model, in the CUSUM graph. That's what you want it to be showing you. If there's other changes that you don't want to be showing up in the model, like for instance, it was an office building, but all of a sudden you got a big data center tenant and you don't want, just a different end use, wiping out all the savings you've gotten because they're more energy intensive, you can do what are called non-routine adjustments to that. So you can still maintain the same baseline, but you can do some non-routine adjustments on that. Those can get a little bit complicated, so we're not getting to those in detail today. But our general guidance on rebaselining is like either if those non-routine adjust, like if the changes are significant, because remember, everything is relative to the baseline period. So if that baseline period, what was going on during that baseline period is no longer relevant to the current situation, that is sort of when you want to rebaseline. And we also say kind of like every 5 years or so, because after 5 years, people aren't really confident that that baseline period is still relevant in terms of things changing. So hopefully that addressed the question a bit. For those that raise the hand on a refresher on what the CUSUM is, the CUSUM stands for the cumulative sum of differences. So what the model does is it takes the actual data and the model will create predicted energy consumption, which allows you to compare actual energy consumption to the predicted value that the model generated. What the CUSUM does is it adds up the differences between the actual and predicted energy consumption of the model, and it adds those up over time. So as you can see in the baseline period for here, this is just the CUSUM. We aren't seeing the before or the actual and predicted. But as you can see during the baseline period, the CUSUM graph is pretty flat and pretty close to zero. And that means there isn't a lot of difference between actual and predicted values. So which is what you want to see in the baseline, because that's when it's being calibrated. So this is saying that it's like, hey, it's pretty good at predicting energy consumption during the baseline period. What this does, because it's adding up the differences between actual and predicted over time, is that it allows us to isolate changes in energy intensity relative to the baseline period from the day-to-day variation in energy use, like weather or other things that are happening in your building. And this is really useful because if you're consistently using less energy than predicted, you'll get a nice straight line like this one, where that Y value at the end is the sum of all energy savings up to that point in time. So the distance on the y-axis tells us how much cumulative savings we've achieved. One thing to note on this one is that the CUSUM is always 0 at the end of the baseline period because of math. So in this chart, the facilities saved 1,500 megawatt hours since the end of the baseline period because it's going to 0 right then. If anyone has questions about any of this as we go along, please feel free to raise your hand and interrupt me. The other thing that is useful to keep in mind is that the Y value of the CUSUM, it's kind of relative because it's always dependent on all the savings that came before. So you can also calculate savings achieved over specific periods just by subtracting the first value from the second value. So in this, you can see that over the course of 6 months, they achieved 750 megawatt hours of energy savings. The next thing that's important to look at on your CUSUM is the slope. So a straight line in any direction means consistent energy use. So not necessarily the absolute values, but consistent like energy intensity relative to heating degree days, cooling degree days, occupancy, whatever's built into the model relative to those independent variables. A horizontal straight line in any means that you're consistently using energy with the same energy intensity as during the baseline period. An upward slope means that you're consistently using energy, using less energy than predicted, so you're seeing increasing savings. And then a downward slope means that you're consistently using more energy than predicted, so you're seeing negative savings or increased energy use. Again, these are all relative to those baseline conditions. So if those operations in your facility change a lot and that baseline is no longer relevant, just remember that this comparison, these slopes are still relative to how things were in the baseline period. Now, I did kind of lie. An upward slope doesn't always mean savings. CUSUMs can use different conventions that impact whether energy savings show up as upwards or downwards slopes. There's no like right way to do it, but it's really important to know what convention your chart is using. So in the ones that I've just been showing, the CUSUM is calculating the difference as the predicted minus actual. So up is energy savings. But for anyone who's using RetScreen, it uses the opposite convention. So it calculates the difference using actual minus predicted. So the downward slope shows energy savings. These two charts, they're using the same data. They both show energy savings. They just have a different convention. So it's really important to understand which is which for whatever software you're using or how it was developed. For today, we're going to be using the convention on the left because we and the energy managers we support often have to communicate this stuff to people who don't understand baseline models. And to a lot of those people, up means good. So we wanted to show energy savings as going up. The next thing to look for in the CUSUM are inflection points. So if we know that the slope tells us how much energy we're saving, then the inflection points where the slope changes indicates when a change in energy use occurred relative to those independent variables. So in a CUSUM, you'll probably see a lot of smaller inflection points that lead to like small or temporary slope changes. In general, you'll usually want to ignore these because they can just be like day-to-day noise, week-to-week changes in energy consumption. And you can spend a lot of time trying to understand those and not get anywhere. So what you really want to focus on are more of those macro changes. So changes that are consistent over a longer period of time or have really significant impacts on energy consumption. Okay, I do have some quiz questions coming up just to reinforce this and introduce some applications of it. But before I get to those, please raise your hand if there's anything about like the CUSUM graph or these things that we're looking to interpret from it that I can clarify or that you're still not sure about. Okay, if not, we're going to jump into it. And we're going to go back to Menti. So pull that up. Hopefully you still have it open on your browser or phone. And our first question is, which of the following indicates that something changed in how you use energy? An upward slope, a downward slope, a change in slope, or a horizontal slope? All right. All right, so we got those coming in as a change in slope, and that is correct. All right, our next question. What does a consistent upward sloping CUSUM indicate? So if you have a consistent CUSUM that's sloping up, is it savings relative to the baseline period, consuming more energy relative to the baseline period, or it depends? Oh, we got two going on. All right. And I think we can interpret both of these as correct answers. I think in general, the correct answer here is it depends on which convention is being used. But as I mentioned, for today, we are using the convention that an upward slope does indicate savings relative to the baseline period. So for the purposes of today's workshop, those are correct answers, but in general, the correct answer is it depends. All right. This one, we're starting to look at an actual CUSUM here. So we have a CUSUM here that's over 2 years. We can see savings increasing. That is the convention for this one. How much total energy was saved by the end of year 2? We have a couple of the Y values highlighted on the chart there. So how much total energy was saved by the end of year 2? Okay. Looks like everyone's getting this one right. All right, that was the warm-up one. That was an easy one. All right. Yeah, so 460. So by the end of year 2, the CUSUM has reached 460 megawatt hours. So that is the total energy that they've saved by the end of year 2 from the starting period. All right. The next question, how much more energy was saved in year 2 than in year 1? So it was 460 by the end of year 2, but that's since the beginning of year 1. So how much more energy was saved in year 2? We've got those answers coming in. All right. And, oh, this one was a bit tricky. So, yeah, the correct answer is 140. So in year 1, they had saved 160 megawatt hours. And then by year 2, they had reached 460. So that means that in year 2 that they had saved 300, but that is 140 megawatt hours more than 160. Maybe that was just the wording. That was a little bit tricky on there. So 300 is the savings that were in year 2, but it's 140 more than what was done in year 1. All right. This one, okay, this one's even trickier. How much energy was saved from projects completed in year 2? 100, 300, 460, or none of the above? And remember on here that, a completed project is likely going to change how you use energy, and changes in energy use on a CUSUM are reflected by inflection points. So the hint on this one is that we're looking at the inflection points here. All right. And before we get to the answer on this, I just say, we didn't really tackle it. So this question was sort of going above and beyond what was just done in the intro there. And from the answers, it looks like it might be some interesting results. Okay, so I'm going to show the answer here, and the answer is actually none of the above. And now I'm going to show how we got that. So here's that chart. And if we want to isolate impact of specific changes, in this case, the projects that went into service in year 2, we need to do a little bit of extrapolation on this because it's not telling us directly. There was the 360, and I think a lot of people said the 100 because that inflection point is where, it was a good interpretation of, we see 3 inflection points which indicates like 3 changes. There's 2 in year 1, there's only 1 in year 2. And so that's when those projects go into service in year 2, and we see those savings there. So I think that's why a lot of people guessed the first option of 100 megawatt hours, because that was 360. But if we want to isolate the impact of that change, what we actually need to do is we need to start off in extrapolating from the end of year 1. So if we look at that slope at the end of year 1 and extrapolate that out, it's sort of continuing on along this slope here. And then using that, we're going to see where that would have ended up at the end of year 2. So that if that slope from the end of year 1 had continued along there, we would have reached 420 megawatt hours. So if we had done nothing in year 2 and we're just still realizing the savings from the work that had happened in year 1, year 2 would have gotten up to 420 megawatt hours. But instead, we did some more projects and turned that slope up even further. So if we want to see the impact of those year 2 changes, it's the difference between those. So it's actually 40 megawatt hours of savings can be attributed to the changes completed in year 2. Does this make sense to everyone? Or hands up if you still have a question about how we got to this answer. Okay, Syed? You want to come off?
Yeah. Yeah. Just can you explain again how we got to 420 from year 1? It means the project started or completed in year 1, and that's where you take the baseline from. I'm not sure if that's what it means.
Yeah. So it looks like in year 1 there were 2 projects, right? These 2 inflection points. And over the course of year 1, we got to 160 megawatt hours by the end of it. But remember, this is like cumulative savings over time. It's not like annualized savings or things like that. So this is those realized savings. And if we didn't do anything after the end of year 1, and we were just continuing to realize the savings from these 2 projects that went into service in year 1, we would expect this CUSUM slope to just keep going straight. So we would expect it, because we're not making any more changes. We've made those changes in year 1. So we're just now expecting that CUSUM to keep going in a straight line, realizing those savings, because this is adding up. We're still counting these savings every day as this CUSUM progresses. So this slope is going up, and it's counting all of the savings that we're realizing from these 2 projects. So we get the 420 by like, okay, well, if we take this slope from the end of year 1, which is, a certain kilowatt hours per day that we're saving because of these first 2 projects, and we extrapolate that out, continuing on the straight line slope, then we would get to 420 megawatt hours of savings at the end of year 2 here, cumulatively. So that's if nothing happened in year 2. Like if we had no slope changes in year 2, if we didn't make any additional changes, that's where we would expect to end up. But we did do another project in year 2, and we started generating even more savings. So that CUSUM slope increased even further, started getting steeper. So we went up even further, and we ended up at 460. And the difference between where we actually ended up and where we think we would have ended up just by extrapolating from the end of year 1, that's what we can attribute to changes made in year 2.
Got it.
Is that clear?
Yeah.
Okay.
Yeah.
All right.
Thanks.
So that's really important, because like that upward slope, it's not like the upward slope isn't counting more projects going on. More projects, more changes are only indicated by the change, that inflection point. So that I think that's something that's really important in interpreting this. I do have a bit on RetScreen on here. Maybe just by a quick show of hands, how many people are using RetScreen to maintain their models? Do we have anyone that's using RetScreen? No, maybe not. Okay. If there isn't anyone who is using RetScreen, I may skip these. if you are using ret screen and just didn't raise your hand, in the participant workbook at the end of it, it does cover the ret screen instructions. Ret screen has some useful tools on here, like, it'll show, you can go see the CUSUM, you can hover over to see the points, the slopes, you can copy the data out to Excel on there. It makes a lot of these things easy in a lot of ways. It makes building these models, if you are generating them, it makes that a lot easier as well. So we use it in that sense. But if no one's actively using it, I'll skip these in the presentation, but you can refer to it in the book. Question from David was the cost of ret screen. Yeah, I think, like Jonathan mentioned, I think it's like 800 or 1,000 a year, somewhere in that range, but you get like 10 licenses with that. So like up to 10 people in your organization can get a license for that cost. But yeah, so if there are any other questions about that, about how you might do this stuff in ret screen, happy to answer those, but otherwise we'll skip over and just keep to the concepts. Okay, so the next thing that we're going to do is, now that we know how to interpret a CUSUM, we're going to look at what we do to change that interpretation of data into action. So often when you're using a baseline model, you'll come across a situation where your CUSUM does something unexpected. Like you'll see a change in slope that you didn't expect to happen. Sometimes it might be going up for showing more savings and you don't know why. Sometimes it might be showing less savings. Like something happened that made you use more energy and you don't know why. Also, sometimes you might expect to see a change in the CUSUM, like, hey, we installed a bunch of higher efficiency pumps, or we installed VFDs, and you expect to see a change, but then there isn't a change when you would expect it. So when something like this happens, we need to figure out why the change in energy use occurred or why it didn't. The first thing that you'll want to do is verify the data. So make sure that it's not garbage in, garbage out, that it's not just an error in data or something that's showing up in the CUSUM. Then you're going to want to characterize that change to get some information, see what information you can get out of it, and then investigate the causes to try to then figure out what's actually doing it. So we're going to look at each of these three things. And maybe to start off, we'll go back to Menti there, and I'd like to hear some ideas, and maybe you've seen this in your own organization, but what could cause errors or inaccurate data? So thinking it's like you're going in, you're updating your model, which, it's energy data. So it could be, daily energy consumption, but it could also be those independent variables, the weather data, or if you're putting in occupancy data or other variables within that. What could be done that might cause errors within that data that could show up in there? Okay, yeah, so data entry error, yep, just an error and putting that in. Calculation errors, we see a bunch of times when like the raw data that you're getting for some of those independent variables in particular needs to be manipulated or some way or aggregated, and sometimes there can be calculation errors within that. Utility bill readings, missing gaps. Also with some utilities, we see this more on the gas side and less so now, but sometimes you still get estimated bills, which can cause issues. Yeah, change in use, typos, not receiving the whole data due to privacy. Oh, that would be a tricky one. One thing that we've seen some interesting ones too of people just changed meters or changed to a different data aggregation system and it did it differently than the old one, and that introduced these kind of errors or inaccuracies in it as well. Yeah, so yeah, if you have the flow meters aren't accurate or things like that, yeah. Faulty meters, exactly. So there are things that can go wrong on the data side. Oh, there's one. Operating parameters that may influence energy, but other than the factor that we analyze. Okay, that is a really important one. We're going to cover that more. I'm going to take that out of this thing of like errors or inaccuracies in the data, because that's the important one we're going to focus on next. But before we start looking for those clues, you just want to make sure that your data is accurate. So look for these kind of errors that have shown up. Excuse me, because you want to rule out that it's bad data before you go through all those steps to investigate the causes, like those other operating parameters. Okay, so now we're going to talk about characterizing the change and using your CUSUM graph to get some information that can help lead us to identifying that change. The first one is looking at timing. So if you look at your CUSUM graph, you see the inflection point. You can go down and see, okay, this is the date that the change occurred. So in this chart, something happened on September 1st that caused that slope to change. But it can also be useful to look at some things other than just the date of that timing. So, this change occurred on September 1st, but, you might also note that that's, late summer, early fall, changing seasons, maybe, if you're a school, changing of operating modes or a university. So that might give some hints, like where in the season it is. You can also note that this was a Sunday of a long weekend. So, okay, like what change could have occurred on the Sunday of a long weekend, which may depend on your organization. Like, does your facility operate over those days? Is it not operating during those days? So that can give you some clues as well. And what we're trying to do in characterizing this change is trying to pull out clues to potential causes of it. The next thing that we look at is the impact. How did that change impact your CUSUM? So in this one, we had a nice slope up showing energy savings, and then that change happened, and all of a sudden we're sloping down, which means we're using more energy than we predicted. Now, so it was a reduction in slope. So we're looking for an unexpected increase in energy use intensity. This is not only reducing energy savings because that slope is reducing, meaning we're using less savings, but that slope turned down so far that it actually went from a positive slope, not just to a less positive slope, but to a negative slope. So that means we went from saving energy to actually consuming more energy than we did in the baseline period. So that gives us some interesting clues as well. The next thing that we can do is look at the scale of the change. So not just what the impact was, but the scale. How much of a change in slope occurred? Now, this one does take a little bit of math that is often outside of programs like RetStream stuff, but we use just the old, slope equals rise over run formula. And we can see that before the change, the slope, we were saving about 3.7 megawatt hours a day. After the change, we were having negative savings of minus 2.5 megawatt hours a day. So this change actually increased our energy consumption by about 6 megawatt hours a day. So now all of a sudden we have some sense of what might have contributed to this, like what equipment could consume 6 megawatt hours a day within our facilities. And you can even, if you divide that by 24 hours, then you're looking by something with the potential to increase demand by at least 250 kilowatts. Now, again, this is all about trying to pick out more clues to help us get to where we want to be in finding the cause of this. The next part of characterization is looking for patterns in it. So these patterns can also give us some more information. If you have a daily model, there might be a weekday weekend pattern like the one we see here where we see it slopes up on weekends, like Saturdays and Sundays, but then the slope is flat or even negative during the week. And this is a pretty consistent pattern that's going on through this time. So that can tell us hey, it might be some change, something different is happening on weekends than is happening during the week. So maybe there's something to do with BAS scheduling or things like that. So that can give us some clues as well. You can also look for seasonal patterns that can indicate that the change occurred in a system that operates periodically, or it's because of conditions that occur periodically. So in this example, we are having these negative savings, and they seem to be occurring during the spring and the fall, while it's maintaining a pretty flat CUSUM during the winter and summer seasons. So it's like, okay, what's different about spring and fall than these other periods? It could be a potential issue where we're having simultaneous heating and cooling happening on this. We don't know for sure. These are just sort of clues that lead us to guesses, hypothesis. It's not going to tell us, but they're the clues on this. Does anyone have any questions about these kinds of characterizations? Or has anyone seen anything like this in the models that you're using? Either the patterns or also some of those other issues that you've maybe had to troubleshoot, like an inflection point that you didn't know about. So I see David, it's like, yes, but cannot explain it. So you had some inflection points, some turn down, but you can't explain what it was. Okay. So what we're going to do, this characterization where we start gathering this information on that change, that's the first step to helping us explain it. And then we're going to look into the investigation part afterwards, right? It's always like reading the tea leaves. I really like that comparison. And sometimes it is. And I think one of the tricky things too is like, as we're learning this and as we're understanding these baseline models and what it's telling us, how do we communicate like what those tea leaves are telling us to others in the organization who we might need to help us identify what those causes are? Brent, I see your hand.
Yeah, I'm just trying to understand the tea leaves, as you just put it very well there. So when the baseline is set, is it like the energy consumed over a whole year divided by 365 days? Like, I'm trying to understand. You mentioned, oh, there's a sawtooth curve, and that was due to weekends. So the baseline isn't normalized to anything. It's not normalized to a day It's not normalized to a season. Is it just average energy per day, or?
So it is. So it is normalized. So let's say in this one, I forget exactly what the details were, but let's say in this one, let's say this flat area is the baseline model, and let's say the model was developed with, say, like cooling degree days and occupancy, but they didn't actually measure occupancy, so they used a like weekday weekend schedule variable in it. So the inputs into the model are cooling degree days and is this a weekday or a weekend? Just like yes, no. So during the baseline period, it does pretty, like you can see the CUSUM is pretty flat, pretty smooth, and so it's like, we're doing a pretty good job of predicting what that daily energy consumption is if we just have those inputs. So we know like for every cooling degree day increase, like on hotter days, for every cooling degree day increase, it's increasing our energy consumption by X amount. And a weekend is going to consume X less energy than a weekday. So, and it's doing a good job of predicting daily energy consumption during that baseline period where we're establishing the baseline.
Gotcha. Yeah.
Now we're in the reporting period, and we see this like macro inflection point here where all of a sudden the slope starts going up. So we're now saving energy relative to that baseline period. So some change was made. But if we start looking micro, and again, like that caution from before, you don't always want to look micro because there's noise in that. But within this micro, there is this pretty consistent pattern where 2 days of upslope and then 5 days of horizontal or negative.
Right.
So that's going on. So what that's telling us is the savings that are contributing to this upward slope are coming from those weekend days, where we're now using less energy on those weekend days than we did during the baseline period. So let's say they put in weekends, like a good explanation for that would be like we put in weekend setbacks on our BAS. So now we're every Saturday, Sunday, we're saving energy, but nothing's happening during the week. And actually, the more concerning part is that a lot of those weekdays are these like downward slopes. So it's like,
Gotcha.
okay, we seem to be less efficient during the week, but more efficient on weekends.
That makes sense. Thanks for that extra clarification.
Okay. Right. Great. So that's what we want to do. And that's like the tea leaf part of this. And again, it's all like back to relative to that baseline period. So it was like good at predicting this, but then something changed that's causing these patterns and these things to happen. All right. So the next step after we've characterized it, so we have gotten some clues because we were like, okay, we know what that impact is, when it happened, the scale of it. Now we need to brainstorm some of the potential causes. And I think, Brent, this goes to your point of like, okay, what, like reading these tea leaves a little bit further. The thing to remember when thinking about potential causes, and I find this is the trickiest thing when trying to explain these baseline models to people who aren't used to reading those tea leaves, is that the model is routinely adjusting its prediction of energy consumption to changes in the independent variables. So as heating degree days, cooling degree days go up and down, the model is adjusting to those if those are one of the independent variables. So it is already accounting for, you know, a warm summer or things like that. So when we're thinking about potential causes to that change in slope, we need to think about what changes other than changes to independent variables could match those characteristics. And there's actually two things to think about in there. And I like to kind of think about it as like, you know, what can the model see? It can only adjust for things that it can see, and it can only see the data we're giving it through those independent variables. So if that CUSUM changes, if there's an inflection point, it's changing because there was a change in something the model can't see and adjust for. So there's two ways to think about this. One is it's due to changes other than the independent variables. So in that example we just looked at with Brent, you know, it's already adjusting between a weekday and a weekend. So it can see when it's a weekend day versus a weekday. So that's not why we're getting the sawtooth, but something changed other than those independent variables. And like a potential explanation there would be like, oh, the BAS setbacks. The model doesn't see what those BAS settings are. So if we change those to, you know, turn more stuff off on the weekend, that's going to start showing up as a change in slope on the model. So those are changes other than the independent variables. The other thing that can happen is when there are changes within the independent variables. So this is where, you know, something about that independent variable changed energy intensity. So there was something that changed in energy intensity without actually changing the values of that independent variable. And this one, it's a bit less common, it's a bit trickier, but does anyone have any guesses or thoughts of like what could be an example of something changing within an independent variable? So it's something about that independent variable changed energy intensity without changing the value that we would be putting into the model. So cooling degree days are an example of ones that it doesn't really do that because, you know, those are pretty straightforward. Although I have seen an example within that. So Sridhar said whether a new holiday, operating hours, right. So if you're only doing weekends and weekends and then a holiday pops up, you know, I'd say that's a variable other than. But one thing on the holidays and schedules that we've seen is sometimes buildings may behave differently over long breaks than short breaks. So if you treat like every, you know, non-operating day the same, but more stuff gets turned off over a 1 week break than gets turned off over a weekend, then you're not changing the independent variable. It's still like, oh no, we still treat this as an off day, but there's a change in energy intensity within that. Weather typically doesn't like falls into the other one. The difference is if you're measuring cooling degree days, but your building is highly impacted by humidity, and then you may have like humidity going up and down, but cooling degree days staying constant. That could be kind of a change within the weather variable that's not showing up. maintenance issues, things like that. I would say like a lot of these ones, the maintenance issues and sudden climate change and things like that. Now, the weather change in a year, normally it should adjust for that. If you have like cooling heating degree days built into your model, it should be adjusting for that. The exception for that is if it's like way out of range. So if your model was built on a cooling degree day range of this, but all of a sudden you have a day where your cooling degree day is like up here, then the model wasn't trained on what happens when cooling degree days are up here. So that can cause problems. One thing of changes within independent variables, like say you have, like, let's say you're an office tower and you're using occupancy as a variable. But what if your tenants change and they're using the space differently? So you're saying it's like, okay, like our space is 70% occupied, now our space is 90% occupied, now it's 60% occupied, and it knows to adjust for that. But what if instead of getting another office tenant, you get a data center tenant? So the occupancy number is still tracking occupancy, but the energy intensity of that new occupant is very different from the other occupants. Yeah, or occupant density. Yeah, so it's like, hey, we're open or this, but there's a lot more people that are coming in. That does happen a lot, particularly when you're using these proxy data, where you may not be measuring the people coming in, just whether you're open or not. Yeah, I see that from David, where COVID lower occupancy saw higher natural gas use. The COVID one was interesting because in a lot of those instances, the models, like the buildings had pretty consistent occupancy, so they didn't build occupancy into the models because it was pretty consistent. It wasn't a routine adjustment that you wanted to make because your occupancy was pretty consistent. But then all of a sudden with COVID, that occupancy dropped and you went from a thing of like our occupancy is pretty consistent to now all of a sudden it's variable and there's all these changes to it. And that gets into this whole other area of like adjusting the model to those situations that didn't occur during the baseline model, when that gets really tricky. Okay. Yeah, I've also heard of the higher natural gas use just because bodies generate heat. And if you don't have those bodies in the building, then, you know, the boiler compensates for that to maintain a certain temperature as well. But yeah, also the ventilation rates made a big impact on that as well. And the outdoor air percentages. Okay, so we're going to go back to Menti and we're going to have a couple of questions related to this to help us narrow in on causes. And again, this is just brainstorming the causes. The next step is connecting it to real world stuff to verify those. But this first example is an office tower. Mid-August, CUSUM shows an increase in energy consumption starting the first week of June. The variables in the model are cooling degree days, heating degree days, and occupancy in the office tower. So what could have caused it? So likely causes of an increase in energy intensity on the CUSUM. The model is adjusting for cooling degree days, heating degree days, and occupancy. What could have caused that CUSUM to show increased energy intensity? All right, we're getting some answers in here. All right, and it seems like the change in use of space is dominating, right? So if I was looking at this model and I saw this happening, I would say, you know, is it because of a warm summer? Well, the model is already adjusting for cooling degree days, so it shouldn't show up as a change in the CUSUM because the model is already adjusting for those cooling degree days. So if it's warm, we're having more cooling degree days, the model should be adjusting for that. So that shouldn't show up in the model unless it was like, you know, drastically different, where like those cooling degree days had never shown up before and the model doesn't know how to handle those, or it causes the building to react differently. Those instances are relatively rare. The summer holidays, similar, it's like that could, summer holidays would definitely impact absolute energy consumption, but the office tower is adjusting for occupancy. Now, we don't really know how they're counting occupancy. Is it just scheduled days or is it actually counting people? So, you know, maybe if it's using a proxy that doesn't actually count people, that could cause it. But something that might be more likely is a change in the use of office space. Out of these three, there's lots of other things that could happen too. But because the nature of that occupancy, the nature of the tenants isn't in those independent variables, the model can't see that, then that could be a likely cause or a potential cause. And I'd say more likely, out of these three, I'd say that's probably more likely than the warm summer or possibly the summer holidays. Because also if more people took summer holidays, we'd maybe expect to see a decrease in energy intensity relative to the occupancy things. But again, these are like hypotheses at this point, and we're looking at like what might be more likely. We can't rule out any of those yet. Our next one is from a skating facility. So CUSUM shows an increase in energy use starting at the beginning of this year's skating season. It is already adjusting for cooling degree days, and it is using the number of ice bookings as a proxy for occupancy. So what could have caused an increase in energy consumption? Fewer ice bookings, a warm fall, or a malfunctioning chiller? Right? We see those answers coming in, and yeah, like the fewer ice bookings, hey, it's already adjusting for that, so we wouldn't expect that to cause the change in the CUSUM. The warm fall, it is adjusting for cooling degree days, so it should be adjusting for that. That shouldn't be causing the change, but the model doesn't see that is the chiller operating well or not. So a malfunctioning chiller would cause a change in the CUSUM, so that could be a likely potential cause there. If you do have any questions or if these aren't clear, please raise your hand and we'll get to your questions and make sure that this is nailed in, because this is really important stuff when it comes to figuring out the causes, like the actual causes of these things. So the next one is a high school. So in this one, a CUSUM shows an increase in energy use during certain weeks during the summer. The model already adjusts for cooling degree days and the school year schedule. So what could have caused it? Community bookings, BAS overrides, or school renovations? All right, this one's a more even split through here. All right, so I think these are all, like, if we look at those independent variables, none of these are captured. All of these things are outside of those independent variables. Like if it's just looking at the school year schedule, it's not going to capture community booking. The BAS overrides, the renovations aren't in there. If we look at those independent variables, all of these could cause those. The fact that it's occurring at certain weeks in the summer, I wouldn't rule any of these out. I would maybe guess community bookings as a potential cause, because like you might have bookings some weeks, certain weeks. BAS overrides, I would maybe see things more consistent rather than like changing on and off, although not necessarily. And same with the school renovations. Like I checked that, it's like if it was one renovation project, then you'd expect to see a change in the CUSUM during that time. But it might be unusual to have renovations this week and then 2 weeks later and then 2 weeks later or something like that. But it can happen. So I wouldn't rule any of these out. I think they're all potential causes that we'd want to investigate further to see what might be the actual cause. All right. So after we've used that model to get these clues, because at this point they're all just clues and hypotheses. So after we've used that model and interpreted the data to get those clues, what are you going to do to find the actual culprit? To find out like what is actually causing that increase in energy consumption. So we've characterized it, we've information that we can use to inform what it might be and what it is likely not. But then we've actually got to do something next to like figure out what it is. And I'll say I've done a lot of work with models, and if you only have the data in the model, That's as far as you can get. You can get to the like hypotheses and like information and clues, but you just looking at the model, you can't find the actual culprit. All right, so we've got some good things here. Discuss with the facility managers, talk to facility operators. Exactly. So talking to staff, it's like, hey, here's like the time when this happened, the pattern that it creates, the scale of that change. Did anything happen around that time that could explain this? Doing a site visit, yeah, great. Especially, you know, some of those potential causes were malfunctioning chiller, things like that. So it's like on those ones, it's like, okay, let's get on site and see what's going on. Is something malfunctioning? Has something changed? We see observing trends, check with the capital projects team. Yeah, looking for those other pieces of information, review maintenance work. Yeah, like some organizations keep like a maintenance log or like a change log of things. So that could be useful to look at, you know, a booking schedules, all that kind of stuff. You want to look for those other pieces of information that might give you more clues and help narrow in to find out what the cause was. The other thing that I don't see here yet is the other piece of data, like even before you go and talk to people that can be useful to characterize it a bit more, is looking at your interval data. So it's like, hey, if you know this change happened in a given day or in a given week, let's go look at the interval data for that day. And then you can narrow it down further. It's like, does it look like it happened the full day? Was it during operating hours, outside of operating hours? That can give you some more clues as well. But yeah, these are all excellent tips on what to do next. Okay, what I'm going to do now is have you practice this on an actual CUSUM. But before I do that, is there anything that came up in our last exercise that you'd like some clarification on? Okay. So what we're going to do, if you could turn to page 7 in your participant workbook, that's where the instructions are. What we're going to do is we're going to look at this case study. So this is a college campus, and you can see the baseline period on the left. This shows both the actual energy consumption in gray and the predicted in gold, and you can see like during the baseline, it's pretty well correlated. Our baseline CUSUM is relatively flat going along here. And what they did, as you can see, they started having some energy savings in their reporting period. So after the baseline ends, they start doing some projects. And I think there's some explanations in the workbook, but it's like, oh, they eliminated simultaneous heating and cooling in the fall. They improved shutdown procedures over the winter break. They made some improved shutdown procedures over reading week and during the like post semester break here. But then all of a sudden, May 16th, the CUSUM turns negative and starts sloping down. So they're looking at like, okay, what caused this? So we're going to have you split into breakout rooms, and within your groups, page 7 has these instructions and the background information on this case study. Page 8 has the CUSUM chart itself. And in your groups, what I want you to do is characterize the CUSUM. So we've given you some information, but then, you know, characterizing the timing, the impact, the scale, if there's any patterns. I want you to, as a group, characterize it and then brainstorm potential causes. All right. We're going to give, Fatima, could we do about like 17 minutes for this breakout? Does anyone have any questions about this activity before we send you off into the breakout rooms? Okay. If you do, raise your hand. We'll launch those breakout rooms in just a second. You can see the countdown timer should be in the top left to keep an eye on how much time you have left. If you need any technical assistance, type in the chat. We'll see that. Sometimes we've realized when we create breakout rooms, sometimes Teams will cause people to disconnect. If that does happen, I apologize. Just please rejoin, and we'll either get you into those rooms or we'll have our own breakout room in the main room here. All right, so we're going to send you off to those breakout rooms. If you haven't gotten the participant workbook yet, it is in the meeting chat that you can click to open it and then download a copy to your computer. All right, and we'll see you back in a little bit. I guess people are just popping back in now. All right. Welcome back, everyone. I'm really excited to hear about what your groups came up with as potential causes, and in the characterization and any questions you had about it. But we've already been on here for a while, so I just we're going to give a quick 5-minute break. And if everyone could come back at 1:30, or wait, what time is it? Your time? 10:32. Then we'll do the debrief at that point. So we'll take a quick 5-minute break and see you back at 10:32. If anyone doesn't want the break and is still hanging around and has any questions about stuff we've covered up till now, we'll be around to answer any of those.
Should take a break too, Jay.
Oh, we had our break when you were out in the rooms doing the work.
I see. So okay, so if you're okay, then I was just checking if there is any way. I used red screen during my masters, but haven't used it since about 3 years now. So is there a trial version or something? I know I've been fighting the management to get the license, keep it out of the process. Yeah.
So you can download the free version of Red Screen and you can use it. It does have limitations on it. And they're like, if you're actually going to be using it, then they're pretty significant. Like you can't save on it. I think you can't connect to the NASA weather data and things like that. So like if you're going to be using it, you kind of need the paid one. But if you want to just sort of like refresh yourself and play around with it a little bit, or like use their examples, or do like there's you could do like project savings quantifications, and if it's not like something you're going to need to save, you can still do that, but with the downloaded free version. But yeah, you need the license for actually like saving your files and doing things like that.
I'll keep fighting the management.
Okay.
Thank you.
Welcome. And I will say, like we use Red Screen a lot. I do like the program a lot from the modeling side. Like a lot of stuff we're doing, it has easy ways to do that in Red Screen, stuff we're looking at today, and that's in the workbook at the end of the workbook there. From the modeling side, a lot of the benefits of Red Screen come in like if you're making a lot of models. Like if you have a portfolio and you need to make models for every school, like it really makes it a lot easier to make these baseline models for multiple facilities than using Excel, just in terms of the time it takes. Now there are the other sides of Red Screen that are useful too, like the project modeling and stuff like that too. But
in our case, we'll be mostly using it for making a business case, since for every small or big project, to start that initial discussions with the property manager or the asset manager,
right.
we get to have a business case there, but it's still pen to paper rather than having it in Red Screen. That
right
could have been easier for us. So
yeah.
In the end, we have the consultants coming in and engineers looking at the facility and then looking at previous historical data and then giving us the report. I would have preferred running it and trying my hand before making a case out of it. So yeah. Okay. Good to know. Thanks.
And Sridhar, I do see your question, and it's a good question, so I'm just going to save it for a minute until others come back. Your other question about Red Screen for benchmarking, maintaining data across various buildings. Red Screen does have a portfolio manager option where like you create a Red Screen file for each building, and then the portfolio manager pulls it together, and you can do portfolio level reporting on there. It's pretty useful for that. You still need to get the data into Red Screen, and it does have features like Red Screen Connects where like it connects to files and you can update those. I think it can take in green button data as well. It can automatically take in like NASA weather data, so you don't have to keep downloading stuff from weather stations. So it is useful on that kind of stuff. We are recording this webinar. We'll get it to Jay Lee. I'm not sure if he sends those out to people as well, but we'll try to get this recording to everyone as well. We'll probably put it up on our YouTube channel, and we can send that link out through Jay as well. Okay, so I'm going to think that everyone's back from the break, and we're going to get into your debrief. But before I do that, Serdar had a question in the chat of how does this curve compensate for the independent variables? Which is a great question. So in this instance, and I think in the case study on page 7, it said what those independent variables are. So cooling degree days, heating degree days, and then it had 3 day type variables. So how these were put in is they're basically binary variables, a 1 or a 0, where it's like if it's a weekend day, then it's a 1. Or if it's a Christmas shutdown, then that variable gets a 1. And when it's not Christmas shutdown, then it's a 0. And what that basically does is, again, it's all calibrated during the baseline period over here. Can you see my mouse when I'm pointing on this, or do I need to bring up the cursor thing? You don't see it? Okay. Is it going to?
I think I can see a mouse. Yeah.
Oh, you see my mouse moving around there? Okay.
Yes.
So during the baseline period, and this is getting more into the building of it, but we have it going up. You can see that weekly pattern, like 5 days, then down over the weekends, and you can see those low points at, here's Christmas holidays, here's one of those post-term breaks at the end of April here. You can see reading week as this lower one here. So just looking at the sort of like daily consumption patterns, you can kind of see what's influencing it. So what the model is basically doing, and then you see like through the winter weeks, it's relatively flat. We get to the summer and you see that increasing because of the cooling load, so cooling degree days. So what the model is basically doing is we put these independent variables into it, and it goes along and it says, it's like, okay, looking at this data, every time we have a weekend, it subtracts, let's say 5 megawatt hours. It's about that. So if we compare like a Wednesday to a Saturday, there's about a 5 megawatt hour difference. So every time that variable indicates that it's a weekend day, we're going to subtract 5 megawatt hours from the consumption. And if it's it behaves, there's 3 schedules in here because the Christmas break and the mid reading week and the inter breaks, they behave a little bit differently. So we have those as separate schedule variables. And then similarly, when it gets to the summer and starts getting hotter, it says like, okay, well, the model detects that for every cooling degree day, it increases energy by a certain amount. So if we have a hot day, you can see the actual energy consumption increasing, and then it uses that cooling degree day variable input to increase the prediction as well. So that's how the model is adjusting to it. So it gets calibrated through this baseline period. It does the regression analysis through here, and it comes up with that equation that's like, okay, for every cooling degree day, add this much energy. For every heating degree day, add this much energy. If it's a weekend, subtract this much. If it's a Christmas break, subtract this much from what it otherwise would have gotten. And so that's how it develops this prediction and how it adjusts and normalizes for the changing situations. And then, as we discussed, the CUSUM is measuring the difference. So as the actual consumption starts dropping below the prediction, the CUSUM shows those savings because it's adding up those differences through there. All right. Covering that, getting to the debrief, who from a group would like to share, some of the, what you did about the characterization? So maybe what did you determine about this change that caused an increase in energy consumption? We get a volunteer from one of the groups to be really brave and go first of what you interpreted from this. And just come off mute and jump right in. Did anyone come up with any potential causes, ideas of what might have caused this increase in energy consumption and energy intensity? Dami? You may have to come off mute there.
I'm going to attempt to do this. Hopefully folks can hear me okay. There's a bit of background noise. Okay. So we determined in our group for breakout group 6 that there are a few things that could be happening here. First of which, the clue is in the very top of the page of page 7, where it talks about changes that were made to account for the shoulder season. We're thinking that maybe during those changes there were some error in the changes that were made, which affects the way the heating and cooling systems behave during that period where we see the steep drop in savings, which is the shoulder season. Should I run through maybe that's one we identified? I can run through the others.
Well, that's health and safety committee.
Okay. What was, like, when you did the characterization, what clues in the characterization sort of led you to that idea?
Honestly, I think it was just reading that, at least from my perspective, maybe someone else from our group wants to jump in, but it was just seeing that clue at the very top that some changes were made at that period. And also just looking at the graph and seeing that that's where the drop in savings happened. Okay.
The fact that that increase in energy intensities started on May 16th, which could be like a change over time or something like that.
Exactly.
Okay. All right. Does anyone else want to share thoughts that they had of potential causes? Sahil.
Yeah. In our group, we discussed the potential of, since that change happened over the summer, the potential of the university having commissioned and started new cooling systems that are now drawing more power than they would have had during the baseline, where potentially they didn't have these cooling systems running.
Oh, like additional cooling systems that weren't there before. Okay, yeah, right. And again, is that mostly because it seems to coincide with kind of the start of the cooling season? Yeah. Okay.
Yes.
And the other thing too is, we talked about it didn't just this is more energy intensive than it was during the baseline period. So yeah, that could support, we put in more systems that do cooling that we didn't have before. So we're actually using more energy per cooling degree day than we would have in that baseline period. Okay. Hudson, I see your hand.
Hi, yeah. So this being a university, and it mentioned on page 7, it includes facilities like labs and sports facilities, but labs in particular, one of the things that are not, one of the variables not accounted for being occupancy, it could include things like, I don't know, summer camp, but another thing could be they started a very energy intensive lab experiment that needs to run continuously for a certain period of time. So like a process change.
Right. Okay. Did anyone quantify the impact of this change, like that scale of the change as part of the characterization? Like how big of a change are we talking about here?
We had a go at that. We figured it was somewhere between 850 and 900 kilowatt hours a day.
Okay.
Which seems
so that's pretty significant then.
Yeah. I mean, we also landed on something to do with, or at least a potential issue is just you've got 14 buildings under 1 meter here. So it could be one change with one of those buildings. The lab example is a great one. We thought potential for different summer events, given that there was a stadium or gym in there. And then not so much related to new cooling equipment, but we thought maybe there could be something around the cooling set point, either the operating hours and or a cooling set point that, while having similar occupancy, is actually doing more cooling.
Great. All right, so these are all great things in the characterization that, like, I think, like, everyone seemed to latch on to that timing, like, beginning of cooling season sort of time. That's a big clue for it right there. I think a lot of people jumped into that. Also potential, like, hey, this is after that spring semester. It could be, different summer usages on there. Like that people calculate the scale of it and realize it's like, hey, this is a fairly significant energy impact to it. That could start narrowing things down too, in terms of like, all right, what buildings or systems on here could have the potential to cause that level of increase in energy consumption. So I think these are really great examples and ideas. What actually happened on this is they did have a bit of a central chiller for a number of the buildings, and they started that up, and there were maintenance issues with it that was causing a pretty significant increase in the energy it used to generate and distribute that cooling to a number of the buildings on site. So I think a lot of those clues were on there, but also like I said, the data that we get out of this, it points us in directions. You never know exactly what it's going to be until you actually get on site and talk to people and start figuring this out of like what could have happened. Let's look at the equipment. Let's see what timing happened. So yeah, so that was very good. Does anyone have any other questions about like this exercise or any of the stuff that's we've sort of touched on before? Dad?
Yeah, I just want to the last point that you mentioned about adding, for example, some chillers or cooling. I'm still a little bit not sure that this could be because of the addition of the saving, because from the baseline definition standpoint, if we are adding some extra equipment, for example, in that we also need to revise the baseline as well. If those equipment is necessary to do that, then based on that new baseline, then we have to judge about the energy saving. I don't know if that makes sense.
Yeah, exactly. So let's say we went out and investigated, and it was, I think someone else mentioned as well, that like maybe they installed air conditioning in buildings that didn't have it before, right? And that's why we're much more energy intensive during the summer here than we were during the baseline, because buildings that didn't have air conditioning during the baseline now do have air conditioning, and they're using a lot more energy. In that case, this is a broken chiller. Okay, let's fix the chiller and straighten this out. But if it's a situation where it was like, hey, we put maybe like some dorm buildings didn't have air conditioning, but we need that air conditioning in there for like health and safety and all of that sort of stuff, then what you would want to do in this situation is do a baseline adjustment for this. Because yeah, you don't want, like, if you're required to do that and you're using this as a tool to highlight energy efficiency improvements, you don't want that required change to be taken away from your energy efficiency efforts that you want showing up on this chart. So yeah, in that case, you would do a baseline adjustment, and there's different approaches to do that. And we don't have, that's a whole other thing on its own that we don't have time to get into, but there's different approaches you can use, but it's essentially what you would do is you would quantify the impact, the energy impact of adding air conditioning to those buildings. And then you would go back and take your baseline data and you would adjust the actual consumption. So your baseline period is now as if all those buildings did have air conditioning during this period. And that's what you're modeled. So then that kind of like will flatten out this slope out here. It won't show up as that decrease on it. But yeah, so if there's a change in use and things like that, and again, remember, because everything here is relative to that baseline period. So if that baseline period, like if the nature of your operations have changed and it's no longer representative of the baseline period, then you either want to rebaseline or make one of those adjustments so that you're comparing like similar operations. So that's a great point there, Bernard.
Thank you.
All right. Okay, so we're going to move on, and again in red screen, you can see the CUSUMs on here. This is that same chart, I believe. I think different setups on there, but it has tools in there to help you with some of these things as well. And you can exclude if there's outliers. One thing that's neat in red screen that's really easy is if you do have outliers, you can easily exclude them from the data so they don't mess up your CUSUM as much. But you do want to understand why they're outliers before you do that to make sure that it makes sense. Before I get into presenting your model effectively, I see the question, what would be the ideal base temperature for calculating HDD and CDD? That's a good point. I think, so in the calculation of those, for those aren't familiar, it's basically you set a reference temperature and then you calculate how many degrees above or below, like above that reference temperature you are, or below for the other one. I think by default, we tend to use 15 for heating degree days and 18 for cooling degree days. That's like the default in red screen, but different buildings may not do that. So you can adjust those. In red screen, there's a really useful tool that like it'll just show you like what a change in that reference temperature will do to the baseline model in terms of improving its stats and predictability. So you can see that, but you never want to like change it unless you have a really good reason for that. So sometimes we see hospitals have a little bit of a lower reference temperature on cooling degree days because of dehumidification and things like that. In extreme, I worked on a mine once where they had heating systems, but it wasn't for space comfort, it was just to keep things from freezing. So the reference temperature on the heating degree days was like 3 degrees Celsius and stuff like that. So I would recommend using the standard 15, 18 unless you have a good real world reason why it's different for that building. All right. So we're going to talk briefly, because I think we've only got about 10 minutes left, about presenting your model effectively. If you remember from the last workshop that we did, we talked about things that make data actionable, making the data accurate, relevant, accessible, timely, providing context, making it clear. There's a refresher of these in the participant workbook, so I'm not going to get into in detail, but it's a particular challenge with baseline models because all the stuff we've done today, you're going to be presenting this to people that don't know this stuff. So they're not going to understand how to interpret this. It's just going to look like a mess of lines and they don't know what they're looking at. So it's really important, particularly when you're using this as a communication tool, to try to provide those. So one thing to do that is to improve the clarity. So there's some things on the CUSUM that might be important to us as energy managers when we're interpreting it. But if you're showing it to someone and trying to figure out like what caused that change, okay, let's get rid of the prediction. Let's have the actual data there, but let's fade it out so that we really highlight the CUSUM and just like make it clear, clean up the axes a bit so that it's much easier to interpret and to show people what we want them to look at. Providing context. They're not going to know what a CUSUM sloping up or down means. So putting some of that context like right on here, putting context of what we're asking them, why it changed in the first place can be really helpful. And then helping make that data relevant. So translating sorry, that circle's a little off point there, but translating that characterization that we did into stuff that might be relevant to them. So it's like, hey, something happened on September 2nd to increase our energy consumption. What could it be? It increased energy consumption by 1,600 kilowatt hours a day. That's about what one of our chillers consume in a day. It's consistently through the week, and it's not due to usual changes in outside temperature or weekly schedules, because that's stuff that's normalized by the model. Here's some ideas of what we think it could be. What else might they know? So it's important to sort of get that context around it and make it relevant for the people that you're talking to. In Rescue, there's an event log. We find this really useful. It's basically putting these things of like annotations on your CUSUM, which makes it also really good as a storytelling tool. It's like, hey, like, look, we did a BAS optimization. Like, you paid a consultant to come in to do that, and then look what happened. We started saving all of this energy. So it's really useful as that storytelling tool as well. I want to have a couple minutes for if there are any additional questions before we wrap it up. But also, I believe before the last workshop, we did register everyone here that's on the commercial SEM program for BC Hydro to our energy management learning platform as part of participating in that program. We have like courses on aspects of energy management there, but there's also a discussion forum. So if you have questions about like your models that you're working with after this, and you want to sort of like post those questions on the forum where, you know, us, our energy coaches, but also peers have access to that to provide input or ideas, please feel free to make use of that. It's a really great peer resource as well as a source of information that's on there. Before we go on, I'm going to look into what Serdar just posted there in terms of the reference temperatures. But does anyone else have any questions about what we covered today, or about like how this might be showing up in your models, or, you know, changes that you saw that you weren't able to explain? Maybe you have some ideas or are looking for some ideas around that. And I do see, Shadar, yeah, the 16, 18, like those are typical usual ones out of there. Oh, for that example with the university chiller, I wasn't directly involved with it. It was, I think it was like pretty significant. Like they started it up and it had been running, but there was issues where with like the distribution system and stuff too. So the chiller was working sorry, like way harder than it should have to provide the cooling that was needed to the different buildings. So I think there were like some issues with like the distribution system on there that was causing the challenge. As always, we do really appreciate your feedback on these sessions. So if you could take a moment with your phone, the QR code, Fatima will drop the direct link in the chat as well. I'm going to pause just for 2 minutes to give you a chance to fill out this form. It's only 4 really short questions, so it should only take 2 minutes on that. If everyone could please take the time to fill that out, I would really appreciate it. We really value your input into these sessions, into making sessions like this better. So we're going to pause here for just a moment. If you have already filled out that form, once you complete filling out that form, if you do have any other questions, please raise your hand or put them in the chat. Okay. And now that hopefully everyone's finished with that, we have one last Menti question before we go, and that is, what will you do in the next week to start getting more value out of your baseline models? So what are you going to do to help with, you know, any of those areas, quantifying savings, identifying opportunities, troubleshooting things, helping with commissioning? So that brings us to the end. If before we leave, if you could finish this last Menti question, and we do have a few minutes left, which I want to have to save at the end of this because I know this is sort of a big topic. It's a very detailed topic. So if anyone else has any questions related to baseline models or their use or any of that, please let me know. We'll be around for the next couple minutes that we have in the session, and potentially longer as well if needed. But thank you all for taking your time today, and hopefully this has been useful. All right. Oh, I like to actually make one. All right, getting started on a model. All right. Love to see that. I find they're very useful tools for energy management and can provide a lot of insight and education into how energy is being used in facilities. All right, thanks, everyone. Start using the CUSUM more often. Yeah, that's when we're doing some SEM programs out here in Ontario as well, where we have like the monthly check-ins and that regular update. Because yeah, that one warehouse that we had where there was a very obvious change that happened, but they didn't pick up on it until 3 or 4 months later. That was really a shame. Sam, I see your hand.
Yeah, thanks, Jay. It's great presentation today. So I just question. So we've been trying to establish our own energy modeling to some of our facilities, but kind of failed at the end because we consider the weather impact and also occupancy impact. But if we include this into our calculation, the result will be very weak because the R square value and also the slope is not appropriate that we should use to establish our model. So in this scenario, what should we do? Do you have any suggestions?
Yeah, and what type of facilities are you in?
So we model our fire stations, leisure centers. So for these facilities, we do have strong connections with natural gas side, but for the electricity, we fail to establish any energy modelings there. So
so it's like a mix of municipal buildings that you're working with?
Yeah.
Okay. So yeah, we didn't cover the building of it on here, but a lot of the stuff that we talked about of like interpreting these patterns, the scale, the impact, goes like we use these techniques when we're building a model as well. Because essentially like if you put in some variable, sorry, I'm just trying to score. Okay, so this is something that like happens sometimes. Like we put in those variables and then it's not a good correlation. Like you said, the R squared is crap. It's really low. So what you're saying is like essentially what's happening with that, like you've put in weather, like for electricity, usually it's cooling degree days. Heating degree days is a bit less rare unless you have like electric heating on there. So those are usually a good place to start. But then once those are in, you want to look at the CUSUM. And it's really useful to do that because that's going to, along with other things, there's other tools in RevScreen that you can use or like looking at things. But basically, you want to find where it's doing a poor job of predicting. So likely if you put in those, what you expect to be the big drivers, and then go look at what is that prediction, what does that poor prediction look like? There's likely going to be some instances where it's reasonably close and some where it's like not at all, and that it's like off. And the trick that you have to do then is thinking about it's like, okay, what are the other drivers that are happening, that are occurring here that we're not capturing that might explain this? And we sort of use that same thing of like, look at the timing of when these things aren't happening, or like when the predictions aren't happening, looking at like sometimes you can see, is it during the week? Is it on weekends? What's the scale? Trying to get clues from the data, and then that same process of going to the site investigation. So we try to get clues from interpreting what we have in the baseline, and then see it's like, oh, it's like, it does a really poor job in the shoulder seasons. Like what's going on in those shoulder seasons that might be different that we're not capturing on this. I'm not sure if that makes any sense.
So you're saying that besides weather and like heating degree days or cooling degree days and occupancies or operating times, so besides these factors, can you give me more about these factors that can influence the result of the energy modeling? Because we've been trying to include daily data, electricity daily data into this calculation, but it doesn't help. So
it's hard to sort of give general stuff on it because it does end up being really building specific. But like for fire, like using fire stations as the example, it's like, okay, if we look at that, I would expect weather to be a pretty significant driver, like cooling degree days if the building's air conditioning has mechanical cooling. And let's say there's no electric heating in there just for the sake of simplicity. So I'm going to expect that cooling degree days is the primary driver. So I'm going to start with a model that looks like that. And then I'm going to see, it's like, where does this not explain the energy consumption? And maybe, I'm actually not that familiar with fire stations, but maybe there is a bit of a weekday weekend, like a 5-day on, 2-day off pattern on here, or like some scheduling or occupancy stuff within the fire hall. It's like, okay, if that's showing up in, like, I'll look at the interval data. If those kind of patterns are in the interval data, let's build that into the model and put in like some schedule or occupancy proxy within that. The other thing that could happen is like looking at, like thinking about that building, what would make one day use more energy than other days? And you can, Fatima, can you just drop my email in there for Certar as well? And then you can also, anyone else, you can reach us through the learning platform if you post on the forum there. Thinking about for that building specifically, what might cause it to use more energy on some days than other days? So for fire hall, it's like, I don't know, are there like big maintenance days where, like, I don't know, they like have these pumps going and clean the trucks or whatever, things like that? Or does going out on a fire call somehow influence energy consumption or things like that? So it's all about trying to find those patterns, looking at that CUSUM and where it does and doesn't do a good job of predicting what the stuff you've already built in can give clues to what those might be. But then you also need to think about the buildings. Like, I know we did an arena and it wasn't working well. Cooling degree days was a big driver, and that explained a bunch. But then occupancy was tricky, and other things weren't really working. And we realized it's like, oh, one of the most energy intensive things that arena does is the ice floods, which is like kind of tied to occupancy because of like the use and stuff like that, but also not really, because sometimes they just like have a schedule for flooding the ice. So it's like, okay, we need to bring that into it. And whether, like, sometimes it's like, oh, we just flood, certain days we flood 3 times, other days we flood 2 times. Sometimes it's like, after every booking. So then it's okay, then we use the booking as an input into it, or whatever. But like, we want to sort of understand that, like, how is energy being used? What's causing that variation in energy? It is a bit of like this iterative investigative process when building a model. I'm not sure if that's helpful.
Yeah, that's helpful. Thank you, Jay. So my last
Okay.
question is that if this energy modeling something required by BC Hydro to include in our SAMP or no?
Oh, I'm sorry, that I don't know. I'm not as familiar with the program rule sides of things. So yeah, I suggest asking Jay Lee about that. My opinion is that it's a very useful tool to do that. Also, if you get that good model, also some buildings just like are hard to model, either because the data on those independent variables that are driving different levels of energies isn't available, or things just change so much, or energy is kind of like random. Like I've seen buildings where it's like, oh, we can't model it because it just uses a bunch of energy all the time and it doesn't vary a lot. Like everything just runs all the time. So it's almost like this like flat line on it. Or in buildings where like what's happening in the building changes a lot. which tends to happen more in manufacturing where you have like product mix changes and things like that. But sometimes it happens in municipal buildings or hospitals. Sometimes those can be a bit tricky.
Yeah. Okay. Thank you very much. Thank you.
Welcome. All right. Is anyone else sticking around for questions, or have you just left your computers and not logged off? If there are other questions, happy to answer those. But if not, have a great rest of the week.
I just got one quick question. Do you do courses in how to build these CUSUMs properly?
We do. I have done a number of training on that. That goes like that has example, like kind of what we did today on the interpreting, but the same thing on like, okay, if you're building a model, what does that investigative process look like, and how do you like kind of what I talked through with Sridhar there, but in like an actual course, yeah.
Yeah, because I see you notice you mentioned things like setting temperatures and things, and I think you said setting like zeros and ones to make sure that like your model ends up at 0 at the end of your baseline. So like I'm only just starting this process, so I'm just trying to make sure that when I start this, it's accurate and not a lot of garbage. So yeah, where would our BC Hydro Energy was it Jade? Would they set us up with one of those courses?
We don't have like on-demand stuff scheduled with Jay at the moment, but you could ask him if it is available, or if they like. I know when they're planning what training should we have next year, they look to what people want to, so you could sort of ask for that. I don't know if they have any ability to do the on-demand kind of stuff like in the short term for it. But yeah, you could let them know that like, hey, this is something we want to learn, and then like he may ask us to do that.
Okay, no, that'd be great. No, thanks.
All right, thanks, Miko. All right. There's nothing else. I think we'll just shut her down now, but thanks for joining and sticking around.
Oh, thank you.
Take care.